ground. Can we stop this gravity? It keeps bringing me down. I can't breathe and I don't wanna die. Can we stop this gravity? 'Cause I don't wanna say goodbye. I forgive the pain you gave to me so long ago. Sleepless nights I laid awake just begging to let go. I almost got to suicidal thoughts, but you stepped in. An angel sent from heaven showed me how to live again. Now I'm falling and I can't see the ground. Can we stop this gravity? It keeps bringing me down. I can't breathe and I don't wanna die. Can we stop this gravity? 'Cause I don't wanna say goodbye. My love, I'm gone. I need to be strong. The darkness had tried to swallow me. Some days I fall, but I hear your call. I pray I don't hit the ground. Gravity. Gravity.
Hello again. Welcome back to the stream. It is Friday where I'm at, and we're going to continue on with the same binary exploitation work that we've been doing in all the previous streams, going through the Nightmare course by the GitHub account Guy in a Tuxedo. The last stream we started doing some format string stuff, and we will finish that out on this stream hopefully if everything goes well. There's only 3 items in the format string section, so it shouldn't, unless we don't solve this one on this stream, then we'll be moving on to array indexing and trying out some of those challenges as well. So yeah, I'm just gonna get into it, I guess. I've already copied in the binary, and if we look at it with file, it's a 32-bit ELF, dynamically linked, not stripped. Okay. The security settings, there is a canary, there is NX enabled, there's no PIE, no rel-row. So canary shouldn't matter for format string because we can just write to arbitrary memory locations, and assuming that we can put that we have enough space in a stack buffer or whatever buffer the printf format string is actually stored in, as long as we have enough space to write, in this case, a 4-byte address in there, as well as maybe a few more bytes for the format specifiers that we need to use, then we can write to an arbitrary memory location. So we're good on that front. PIE not enabled, or it's not compiled as a PIE executable. We have the ability then to figure out addresses in the global offset table or just elsewhere within the binary itself. What do we link to since it's dynamically linked? Linux gate. That one I don't know what it's about. And then libc. Let's find out about Linux-gate. It looks like maybe it's a more interesting. Oh, is this how they do VDSO stuff? Maybe on 32-bit? Okay. Yeah, it's for doing the virtual syscall stuff. Okay, that makes sense. Not gonna worry about that. All right, so let's just go ahead and run the program. That's my name. Okay, and then we run it with %p. We get a pointer. %n. We get a core dump. Cool. Then what do we want to do? And write in and do we get 4 1s? No. Or like the hex bytes 4-1. Just gonna copy 4 of those. And there are our 41, 41, 41s. It is offset a bit. So maybe if we did I don't know if we have the ability to trigger to like get, so the issue that I'm looking at, let's see, we're at like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So if we do, oops, AAAA, then percent 11p and percent $12p, we can see we have 2 of the A bytes in the upper word of this D word, and then the other 2 in the lower word of the second D word. So basically where these A's show up is offset from where our pointer reads on the stack are going. I guess that's not so much of an issue because we'll just space it out too. Like we could do, and then there we go. Okay. So if we put 2 spaces or 2 characters or whatever, then the next 4 is the address that we can read. Okay. Then we need to pop it open in, let's do it with GDB just to stick with what we were doing previous ones. List the functions, see if there's anything interesting. What is the NAO function? This call system with maybe that string. Oops, didn't copy it. That's okay. So what we need to do is get our string. So let's do like, if we're gonna create a flag, then our string needs to be where the stack pointer is. Can we do that? Supposing we're going to call the system function, or basically so we could control the return pointer and have that go to, oh, we could also write this address, I suppose. Write to the stuff at this address. How can we do that? Okay, so if our string is like cat flag .txt and then other stuff, do we need, oops, we need the space there, but if we just comment out the remainder of that line, then putting the address that we are printing into, I think. Or is that that string is probably the like happy face. Don't ignore. Oh, okay. No, that's just a. Oh, I was not looking at the control flow. This is if we don't enter anything, I suppose. Okay. So that string. Yeah. So we snprintf, or just sprintf, onto the stack. Do we have pointer? So in theory, even after our printf, top of the stack is going to be the string that we've constructed with the sprintf and putting in. This isn't guaranteed, because I think printf isn't necessarily going to clean up the stack for us, and we might be skipping that because we know that we're about to jump to exiting the function anyways. Although, I don't know, they seem to be assuming a fixed address. So, yeah, so, okay, let's assume that top of the stack has the same string that printf receives as its first parameter. Then, when we call system, as long as that string starts with like cat flag, space, pound, then the other stuff, then we should be okay. So let's see, this is like the first, this will be at 12. And then this will be 13, 14, 15. So I think if I put like AAAA here, and then %15n. So let's say that's our input for now. We need more stuff, but let's assume that's our input. Then okay, interesting. Oh, I want P instead. I just want to print that out. So that does get the 4 A's as the pointer. Okay, so then our pointer can go right here. We can access it at address 15. And that is... Oh, you know what? I don't think we even need to do something where we overwrite this. We can jump to this address. So we just need to write this pointer to... We need to write this value, rather. To whatever is on the stack for the return. So it's going to be (9C). Yeah. So maybe A4. Hey Julian, how's it going? So working on the last format string challenge. So let's do like percent. If the beginning of this string, which is at 1C, was 11 or 12, I guess. Then we need to add, what is it? 9 by 4, 36 plus 11. Let's do like percent 46 p percent 40 or 45p 46p 47p 48p. Okay, are any of these? Okay. Oops. Let's do 49. So I'm trying to find the stack canary, right? That'll be pushed at 9C, which is basically the very end of the stack frame, whichever side you want to call it, the beginning or the end. But it's right up against where EBP was pushed. And after that is the return pointer. So, and that's going to be like a random value. So I'm looking for something that looks a little more random than these do, basically. Alternatively, I could run it in GDB, look at what the return pointer is, and then try to find that return pointer. Maybe that's what I'll do. Yeah, why not? And then we can write a little fuzzer script to find it. So all right, so ESP has this address. Yeah, same address every time. Okay. Oh, that's not going to be the case with it'll at least be like, it'll have those 3 digits at the end. Those 3 hex digits. Pretty sure. So let's try that. And start at 1 while I less than let's assume it's within 100. Do we want to, I guess we need to start the process again each time. And I think it's like that. Let's do it real simple. Let me double check. Okay. I'm gonna say something like that. And let's just call it I. Okay, fair enough. Okay, I didn't print out. And yeah, it was a different address that time. Okay. Okay. But it's always 43. Cool. I'm okay with that then. So our index for the return address is 43. So then exploit it. We want to is it going to load the oh yeah, okay. So first we're going to add cat flag.txt. That is our command we send to system. Everything after that will be a comment, so we can add whatever we want into the payload. And the first thing we need to do is wait, okay, I've been thinking about this wrong because we need the stack address, not the actual return value address. We need the address of that on the stack. Which can we get that? So it could be the same every time. I wouldn't think so. I guess I can just open it in GDB. And then continue. Why did we get the syscall? Oh, because we didn't. All right, so ESP is this address. FF8 D4 23C. Okay. Yeah. So stack is located at different places on each run. So I can't just figure out, I don't think I can easily figure out the stack address and write to that. Well, I might be able to leak it, but if I don't have the ability to send multiple pieces of input, so even though we could leak stack addresses from this frame and then calculate the offset and have it be pretty reliable, I don't think we have the ability to what am I saying? Don't think I have the ability to actually make use of that leak. So I want to call to system, right? Well, it's going to call puts, so I guess we can overwrite the puts address with the address of now, or the target address, which is just right here. The problem is by the time puts happens, oh, and we're not going to do puts because we're going to jump over it, right? So we're going to, I guess we could do the stack check fail. That doesn't change ESP at all, but we would have to modify the stack check. I guess that's one way to go about it. Or not modify the stack check, but we modify the canary so that the stack check fails. And then when it calls the stack check fail PLT function stub, it will jump to right to the call to system. We could either put the system address in there, or we could put the address of the call to system in there, which I think is simpler. So yeah, that's feels doable. Okay, so we need to see what is at the address 2 prior to the return address. So I would think $41 $P. That seems wrong. Right? Yeah. Guess there's a null there. Unless the canary is particularly unusual in this program, those don't look like Random values. That looks like it might be a random value. Yeah. Okay, so that's the canary. So we write something to that. And we write to the address that's in GOT entry for stack check fail. And I think we have to write the full 4 bytes because it's probably null since we won't have called it before. That should be fine. Okay, so let's see. Let's have that at some point. All right. Now we need payload to have, don't really care what we ended up writing to the canary. Let's double check that this, if we do like $39n, that, it doesn't trigger the canary. Let's do or you can do that. I actually want to kill the child. And then 117. Why are we in the syscall? Why is that a breakpoint that I have? Gotta hang up? Oh, because we okay, we'll just do no? So we need send line. Okay, so what? We get a seg fault in printing to, oh, because I didn't have the address in there. Right? What is the address we were trying to write to? EAX. Oh. Again, yeah, I keep like the model that I have in my head of how this should work is messing up. We need to have a number on the stack that is the address that we can write to. And I don't know the address of the stack stuff, so okay. So yeah, we can't force the canary to be wrong. I mean, maybe we can overflow. I don't know how big that buffer was. I think it was very big. No. Okay, so it does not overflow to hit the canary. At least I'm pretty sure it doesn't. Yeah. Okay. So what else can we do? I guess we could. It's pretty annoying. But we could write our command so we could literally call to this address, not the system call, but the one that loads this into ESP. And there's just a fixed string here. We could overwrite it with like cat flag.txt space pound, and then it doesn't matter what the rest of the string is. So that's the one thing I can think of remaining. And then we override. Well, we don't have another function that's going to get called. Another imported function or anything. So that's tough, actually. Maybe, I mean, that's really the issue that I've been dancing around and not seeing it more clearly is overriding the stack check doesn't matter because we aren't hitting that. Overriding puts doesn't matter because we are not going to run that code either. We're going to jump past it. So we're jumping away past both of the calls that we could do after the printf that enables us to write memory. How do I know? Can I know what's like the address of the stack? I don't think so. Maybe we could figure out what GS offset 14 is. I don't really know, like maybe we could trigger the stack canary not by setting the value that's on the stack, but by setting the original value. I gotta be honest, I don't know how the like segment offset stuff is calculated. If we run this, what? 10.04.278. And then no. Okay, we want to just okay. So GS is 63. That's like the index in some table, I guess, or is it just multiplied by a fixed value? Segment descriptor. Oh, memory segmentation. So it is just multiplied by 16. Is that accurate? Well, we can give it a shot in GDB. So what do we want to look at? Yeah, that seems way too low. So I think the selector must be an index into some table of the actual addresses. Can I just say like can I get that value? Just have GDB tell me. Okay, so we will just catch that syscall when we run the program. And it's going to move EAX into GS. What? There we go. So EAX at this point is literally 63. Like, does not help me. Oh, God damn it. I don't know. This is maybe the wrong way to go about it. Just not. Like, it's going to be talking about the canary that is stored in the stack frame, in the function frame. How would I phrase this? Okay. Oops. Is there any chance I can print that out? No. Okay. But I need. Like, I need to actually execute memory to be able to, or execute some instructions to be able to locate that. To put ampersand on there. No, this is in the ARM stuff. Okay. I'm gonna not keep going down that route. This surely is more simple than I am making it out to be, but I think, I mean, I'm assuming that, yeah, can't write to the executable code segment, so can't just like arbitrarily change these instructions. Julian, if you have any ideas, I'm all ears for ways to potentially make use of this format string vulnerability. I mean, obviously I would think the idea is to be able to run that system function call rather, from this other function. But I would have to have it. This is the only call that I can think of how to get it to actually trigger a call to an address using an address that I can overwrite. What are the other functions that we have? Like where is stirchar stirlen being called? Okay. I don't think this is, yeah, this isn't going to work probably, but Okay. I was sort of hoping there was some exit procedure that would call a function from the PLT, but I didn't see anything. Oh, now we get all the functions from. That doesn't help me. What? Greeting. Certainly curious where Sterling is called. Can I do this? Does that help at all? Type matching. Okay. What do I do? They're like. Or maybe I can. Will it show me? Just we do this in get inline, okay. But we've already done that code. It's not going to happen again. Okay. But with a buffer size of 40, yeah, 40 hicks, and it does not overflow that, so or wouldn't that, and it's not going to overflow enough to cause a problem? So what I'm thinking right now, and this is almost certainly not relevant, but we have 40 hex bytes that we read into a buffer at 5C, ESP plus 5C. So that takes us from 5C to 9C. That's our buffer for the actual direct input from the user. Then we sprintf that using this format string, which has a prefix bit of text and then a %s. And so we could potentially insert those 40 hex bytes at 64 bytes into this string, and we are writing that to an address that's at 1C, and there's only 64 bytes between this and the start of the buffer for the thing that we were, yeah, but it doesn't really, like, we've already read past that part of the buffer if we overflow it. I do think that we could overflow the buffer that the print, that the sprintf writes into, but I don't think we can overflow it in any sort of meaningful way, basically. Yeah. Kind of at a loss on this one. I thought I was pretty certain to be able to finish this this last one in this stream, but I cannot think of anything. Can't think of any way to overflow to trigger the stack canary. Well, okay. I'm gonna just spitball a little bit here. If there is an address on the stack, if there's like some data that's on the stack, which we can then access through printf, and the data in that location is a stack address, some pointer that's, you know, within this stack frame, and we know it has a fixed offset relative to where we push the canary or even just did the return address location, could we use %n to first modify like the low byte of that address such that we add to it the offset that we need. And then, because it's really going to be the high bytes that are going to be different, the higher bytes of those 4 bytes of the address, that'll be different based on the stack being randomly laid out. So if the low byte, for example, in the best case scenario, it's a difference of less than 256 basically, then we can modify that low byte and not need to worry about maybe the second to lowest byte, but potentially we might have to modify both of those. Then we can again use that address, but now we would need a pointer to an address that's on the stack that we also then know where that is, and we don't know where that is. So I don't think that helps me. Can we do that? It would have to be, yeah. If we had something on the stack which had its own address, then that might have worked, that idea. Where like, because if we do %n using that as the address, then it's going to overwrite itself and we can use a %n again on it. But don't think that's going to be the case. Maybe the offset. No. Where do we start seeing space? Fix that up. Oh, let's do it this way. Not enough. Okay, so this is where we have 4 and 4 1. These other values are not helpful. Okay. Hello again. I haven't really made any progress other than I've just become more despondent that I have no idea how I can solve this one. The general situation is that this is our printf where we can overwrite memory. This, and maybe I need to look in here, but I don't think we are reading in the flag or anything and storing it like that first challenge. So we can write memory with the %f here, and then we jump to the stack canary check. If the stack canary check fails, then we can call an imported function, and our memory write would allow us to control that. Otherwise, we just go and return, and we're done with the function. So I don't know what we can do, because it does not seem like we can get the stack canary check to fail. I don't see how we can overflow the buffers that we have and write to the stack canary. Right, but if you leak something, that's only going to leak after that. Like, I don't see how we get more input after the leak. I can leak addresses on the stack for sure. And then if I know the stack, an address on the stack, I could calculate an offset and like override the return pointer wherever that's stored on the stack. But leaking something from the stack, I think, please correct me if I'm wrong, if I leak something with this call to printf, we don't have another input to then do, like, we don't have a way to read that output and then still have it impact on what we are telling printf to do, is my thinking. Yeah, NX is enabled, so can't just write to this code and have it do something else instead. And there's no rel row, so I mean we could definitely write to the GOT, but it doesn't end up getting used again, it seems like. Because after return, we basically just go directly to exit, and we're returning into libc already. So the calls to exit and other stuff aren't going to go through an indirection layer. It's not going to use a GOT or anything. What can we? Yeah, I've been trying to hold myself to not doing that as much as possible until I've exhausted all my potential options. But I actually really, I think I might be at the point where I can't think of how this should be done. I'm gonna look in the get and line again just in case there's something that I am missing. No, it just calls fgets, and then if we have a new line, it nulls it out there. So that's the end of the string. So we don't include the new line in the stuff that we put into here with sprintf. Okay. Yeah, I guess I'm gonna look at the write-up because I got no clue on this one at this point. Let's look at the C code in case something pops out to me there. Like, unless you happen to know how we could work out the address of the GS offset, or like basically where the memory for the stack canary original value is stored. Because if we can figure that out and it's writable, then we can write to that. But I don't understand how that information is set up, I guess. You know what? Let me keep looking into that. Now that I had gone down that path and then said, like, this seems like I'm going too far in somewhere that's not helpful. But what I want is glibc setup stack canary. So I want to actually, well, it's not going to really, oops, yeah, where do we do the, okay, so we're in the function where we set the thread area. And not going to jump. ESP has just C in it. So, is there anything meaningful there? Let's look at the move instruction. Yeah, I know. I just forget to do it that way. Because maybe this will specify control registers, maybe. Allows to say actually what's the bytes for this instruction? Can we see it is 2 bytes starting there. 8E E8. Okay. So if I had to guess, the actual address that's in the segment descriptor associated with the selector value that is in GS is going to be not static, I guess. Okay. Maybe it's set up by the kernel. Oh, it's in the task state segment. That just has what the I don't know. I don't think I have any access to that memory, is my guess then. That it's just like not mapped in the virtual memory map for the process. And it's therefore only accessible through those commands. So, okay. Yeah, let's see. Scans the input. Okay, so they came to the same conclusion that that's the only one that gets called. And they can't override the buffer. Oh. I thought there was no finish, or like there was nothing being called from that. Because whatever. So if we set a breakpoint on the return from main, and then we run the function, don't care about the setting up the stack canary stuff, or the realistically the thread info. So we hit the return, and then we do SI. Maybe that was my issue. Maybe I was stepping incorrectly. Okay. Yeah, so what the heck? So I guess at some point it is getting the, right, now it's gonna run the destructors. Okay. I think, so I had this thought when I was earlier, basically, which is after we return from main, we go back into libc, and libc has, if you call the like add exit function, that's how you can set up a function that will run when exit happens. And it stores those in an array called dot finish array, I guess. And so for some reason, as I was stepping through it, I was using NI instead of SI. So we stepped over the exit call, and it didn't seem like it, I don't know. I was being kind of sloppy there, I guess, and I missed the fact that we can totally get it to run a function when exit happens. So we need to figure out where that is at, I guess. I don't think it's going to print it for us here, but maybe if we do R2. So it's at a particular section, I guess. Yeah, so this address, if we, let's run it in GDB, and do like 4 words at that address. So we've got one entry. I'm wondering what that is. Is that actual code? Okay. So this does something or other. So if we do this address, we throw this address into the next entry in the array. There we go. Now it's printing it as full. So we put this here and maybe write a 0 there. Or even just replace this first one with this address. Where is it? Here. Then that's probably easiest because We only need to write the low 2 bytes. Okay. So, how do I write memory in GDB? Okay. Do the Stack Overflow one. Okay. With set. So if we say we do this as word, this address is equal to this address? No? Am I misunderstanding that? Do it as int? Okay. So then if we look at that, we've got our address of the call to the system PLT, and if we continue, now it tries to run it with whatever was at ESP at the time. But ESP, okay, so we need to go to this one and force writing that address, I guess. Okay, so let's see, we want command is going to be equal to, actually, yeah. What? Oh, of course. We'll figure out the payload later. That's the command we want to use. We need to write that to the memory for this string, I guess. Maybe there's a simpler way to do it, but this is how I'm going to do it, and then we'll go through the walkthrough the remainder of it to see what they actually did. Which means I need to say command do this as string, do it as bytes instead, maybe. So the first section is going to be I guess if we just do it as bytes, then we can get, that'll be 4, that'll be 4, that'll be 4. We can do it that way, or okay. I think that's fine because the length of that string, is longer, yeah. It's rather annoying though. Because we're gonna have to write it byte by byte, I guess. Ooh, okay. Oh, I don't need to worry about it in amounts of 4. because we are going to be writing it byte by byte. So we need like, so the payload will start as this, and then for B in, for I in range when B, we are going to take do that? No. Just do this. Why is that? Oh yeah, okay. Because that's decimal. Okay. So our payload needs to have we'll do the payload later. Oops. No. Okay. We'll have adders as an array. And target string is this address. So we need to put the address for each of these bytes. That's going to be interesting. It's 14 times 4. We don't have enough space to do that. So this is not how we can do it. How do we get so we're going to call system. System wants the stack to be a pointer, the top of the stack to be a pointer to the string that we will be using. But we don't know, like if we call it through this mechanism, then we know that this string is what we're going to do, but we don't have enough, I think, we don't have enough space in our buffer to write stuff that will, like, unless we actually do it in blocks of 2, right? We really need half of the space, roughly, but we're gonna, or, sorry, it's gonna be, I mean, it'll work out to the same amount of space, right? But we'll need 7 4-byte addresses. Still pretty bad. the minimum we could do to get that string in is 4. So let's try it with 7, I guess. Range is okay. So do it that way, and then put our command is gonna be, and we don't do that, right? We do like append. Percent. So we need to figure out what number I don't know. Let's just call it V for value. Terrible naming. So we want command V I through I plus 2. And we want to pack that as a number. Right. If we do oh, we need to unpack it, I guess. Yeah. Okay. Is that what we need? To write that. Yeah, I think that'll work. So you could burn an address to make the first one work easily, but how much will we have written? Okay, and our payload needs to start with like 2 spaces. This is probably the wrong way to go about this still, but that's what I'm gonna go with for now. So on the in the first entry, we're going to assume that we have written, so we're doing 7 by 4, so it's 2 plus ooh, that's going to be, yeah, I think we're okay there. makes sense. Interesting. Or, sorry, we want it the other way around. Okay. So, yeah. What do we want? I don't care. We're gonna do 3, and then v minus has written. I want to do this. So I divide by 2 plus 11, I think. It's pretty fucking gnarly. Yeah. Okay, and then after the printf call, do that. When did it not? Oh, we need to send a line. Okay, so let's see where we wrote to. Didn't segfault, so in theory we didn't write to the wrong place. What do we want to do now? But we didn't write to the right place, I guess. Oh, because we didn't actually do anything with our payload. And let's print out whatever. Okay. So for a in adders, payload plus equals pack the address. For C in commands, payload plus equals, just have it all be bytes. No, because I don't think we can call format on bytes. Maybe we can, but I'm not gonna bother with that. C dot encode as bytes. Okay. This is surely gonna be bad. did get a segfault. So where are we trying to write to? This address? Why are we trying to write to that address? 6175, which is, that's A, but that's not C. I don't know what we're trying to write there then. And why can't we write to that address? Is that in read-only memory or something? Looking at 48.7. Oh, yeah. Okay. Right, and this address as well is also in read-only memory, of course, because why would they be in a writable segment? They're fixed strings. So how can we get okay, I have a better idea, much better idea. The printf call I guess it is not much better actually, because again, like, the stack has changed around by the time the finish function happens. So we can use finish to call main again, I guess. I don't know how much that helps us. So we need to get I guess we would have to do sprintf anyways, but is that right? No, we need this is tough, because if we're going to override a GOT entry with, say, call to system, it wants the value at ESP, whatever ESP points at, to be a pointer to the string for the command. And our string is just somewhere on the stack, and we don't necessarily have any instructions we can jump to which are going to put that address at the top of the stack. We don't have any addresses. Again, nothing is jumping out to me on how to even make use of the system function given our circumstance. Right, like I'm pretty sure if I call greeting and we say we set the 139, set the breakpoint to return, and then we do the set disable now or disassemble now there. Call set integer and set it to 72 and then continue running. It'll run the system call that has been hard coded to run. So just need to work out how to okay. It might be possible to do some manner of sort of like a ROP chain kind of thing. Oh. So what I'm seeing here, we have move EAX into the top of the stack and then call something. We could make this a call to system. So if we can control EAX and have it point at our input buffer, then having a finish function that goes to this location or this location, either of them, and having overwritten the system or the set buff GOT to be system, that will call system on our buffer. And our buffer is at this address. And obviously this loads it, but does that the problem is getting a call that we can control where EAX will have the value that we want. Maybe if we can find a gadget that pops two things off of the stack. So if we were to call to this address, then no, that doesn't really help. God damn. I'm not able to figure this out. I'm running out of time too. I don't know. Any suggestions from chat? So fundamentally, we need ESP, whatever is pointed to by ESP, to be an address that is this stack buffer, basically. But we don't have like arbitrary jump around kind of capabilities. What if it's the first thing that happens in AX is the second? Okay. So the problem, if we jump into the middle of this, ESP is not going to be pointing to where we want it to point, though, for this load instruction to work. Pretty sure. But oh, we could do that though. Okay, maybe this is simpler than I thought. If we patch So we overwrite the GOT entry for strchar, which takes as its first parameter the string to search through. So we make that system, and then our finish function, basically, we could go back to main. Doesn't really matter. It's probably simple to go back to main because this will set up a stack frame that has sufficient space. That stack buffer gets passed into get nline. We call fgets, which will then take in our command, and then when it calls strchar, it's really calling system on that command. Okay, let's do it that way. Alright, so all of this nonsense, we'll leave the command in there. Doesn't matter. So the first thing we need to do is overwrite strchar, and then we will overwrite the finish address. So we can do that. We'll get the GOT entry. We need to, it will have written that already. We'll have loaded it at some address that we need to fully replace, I think, because it's not going to share any bytes. Is it accurate? Probably. Oh, well, I guess. Okay. You know what that we want. Right, we want the PLT of system, I guess. We want to write into the GOT entry to jump to. Just write the PLT entry for system. It will have been called already. I guess it doesn't matter if it was called or not, but sure, why not? Okay. So we need to write all 4 bytes of that address. We need to figure out how to write that properly. I guess I could have saved the same sort of structure from before, but oh well. So for each byte in the length of the system PLT 32-bit. I mean, really, I know it's going to be 4. So let's just simplify. Then we want to do throw the address of stirchar GOT entry in there, and we need to write that. What was I doing before? I needed to have percent. Oh yeah. We'll do that, and then I go back to what I had before. Yeah, I was just forcing. Okay, I didn't need to use a format variable for the 3. So then we want let's do like get the bytes from that address, and we'll index into it as I. Or sorry, that, and then where has written is going to be equal to 2 for the beginning of our. We need to offset the payload by 2 plus 16, I guess, because for now we're going to write 4 addresses, 1 for each byte that we're overwriting, and they're 4 each, so we will have written 16 bytes before we get to this string, I think. Okay. Then that goes back to 0. So we say oh, do we need to put the command in first? No, we'll do the command stuff later. That's right. Okay, so probably don't even need. I'm going to create the payload up here. Payload. And then for A and adders. see what that looks like. Okay. What are we doing wrong here? Where is it? There's no encode from U32 PLT. Yeah. There's no format on bytes. Okay. Oh, that's right. I thought about doing that before and then decided not to. Interesting. Expected string of length 1, but int was found. Okay. Why is this? What does that look like? And then, so, oops. We do okay. Guess you get an int by indexing into bytes. So we do this address, this one, and the value that we want to write is those bytes. Okay, so first we need to write a 90, then an 84, a 4, and an 8. Okay. I mean, in theory, this would actually overwrite that entry. Maybe this could work. How long is that string? That string seems way too long, though. Like we might need to. $66 bytes, a little bit too much. Damn. How can we make it shorter? I guess we can take out the $3 sign. I don't know that we need that part. Might not even need the spaces. But we won't have enough space then to write in the so to do it in twos, I guess. 2 byte portions. This again seems like more than it needs to be. Okay. If we do right. word. So U16. That. That's going to be too long just from printing out the... Oh, it's actually shorter. Okay, interesting. What does it look like? So it's a lot, for sure. Then we've got, yeah, but still shorter. So I just need to be okay with that. Oops. Didn't actually need to run the exploit. What we got here? So we can see if that actually worked. And then we might have space to do the other one. Do we even need the space there? 142. No. We make sure that we have the space in there. Looks like false. Okay. Interesting. What is the address we're trying to write to? 804A9P. Or, sorry, 804-9A. And then whatever that. Okay. So that should be in the read-write segment. So we're segfaulting, trying to write the wrong address. We're indexing incorrectly. Getting spaces. Why is it 3 spaces? Oops. It should be, if we take this out, what does it look like when we run it? Now we've got 9A in there. 9850, okay. So we want those 2 spaces, but maybe we're off. Oh, it's not 11, it's 12. Or not. 3, 3. What does that look like if we do it that way? Are we putting in the address the wrong way? That looks like a valid address, it's just incorrectly. Like, is that 80? So what's the 52 about? Oh, that's, yeah. So the 50 should be in there. Then, what the heck? Oh, it's still trying to, okay, so this is the start of the next one, or the previous one, the end of the previous one, I guess. But if we push it out by 1, let's say, then we're getting the space in there. No, didn't want to do that. Now we are getting, okay, so why doesn't this work if we add the one more byte? Or maybe that's it working and we are putting the wrong stuff in there. It is at a, well, these are all different addresses. God damn it. So if we do space there, let's say. Okay. So why is this not working? Let's run it again. We'll see that 2 spaces and then the A's means that we are using those A's as the address for where to write to. But then when we take them out, and it's just these 4 bytes. That's not the address that it tries to write to. So what the hell? What the hell? Oh, okay. It's not the first write that's failing. It's the, oops, the second one. This needs to be I divided by 2. Okay. So I think that is writing. We can verify that though. And what is the GOT address? I don't know. Disassemble. jar. What does that get in line? And then okay. Has that address? Maybe that's no. Okay. Did we write the wrong address? So we'll just do one at a time. So where's that? 4A? Did I miss one? Yeah, okay. So 4A has that address. Oh, no, because I'm off. Sorry, it is 4.8. Right? Okay. What one I'd expect. Then stir jar has this address in it. So we didn't write it. Where did we write to? What did we write? Let's put it after, right before the call and then after the call, I guess. Okay, so we can look at, I think it's 50. Yeah. Has that address in it. And write to 50 and then 52. Oh, we need to HN, I guess. Let's do that. So we'll see. It has that address. Step over the printf. And it still has that address. Is that right? Okay. So then what did we write to? What did we write to? I mean, we could just do it without the numbers and see if that impacts anything, but it doesn't seem like we're actually writing to that address. Oh, that's weird. Oh, because it's that way? Okay. Okay, so we have written something there. I don't think it is the correct value. I'm sure it's not the correct value. Right, because what is the one at 48? Yeah. What is the PLT that we want to write? We don't want to write this address. We want to write... No, that's fine. What is, and write this address, yeah. So we're getting it quite wrong. So if we take out those spaces, okay, so that still works, and we don't need we can save a little bit in our string. Okay, let's take out oops, not that part. Okay. So we've got E4 is what we've already written, and then afterwards we've got 80 or got 80 is what we've written the first time. And E4 is the second time. Which is weird because written 128 from the last one. Oh, it doesn't actually. Okay. So has written is going to be 28. Does that work? What does that look like? Okay. And negative. Right, I don't want the maybe. Okay. Then what is the address of yeah, okay. So now we have written system wherever I printed out. There we go. Okay, so then we need to what was the address of the finish? I need to find it in radar again. This address. Okay. Then we want that address. And this goes up by 4, so 32 bytes. What we want to put in there is it's going to be 36. We'll do the same thing here. So this spot, whatever. Oh no, we can call this pet. I think. Or Yeah. Let's double check that that works. Too long. God damn it. How can we fix this? We know that okay. Well, shit, but we'd have to leak the address. Trying to see if we can save on any bytes that we can write. If we really have to write a full 4-byte thing. It's pretty gnarly. So the address that we need to get into that array is this one. That's the address we need to write to. Which has that address in it. Is that accurate? Oh, so maybe we don't need to write very much into that one actually. Maybe just the low byte. Oops. Yeah, okay. And then main is here. So we only need to write the low single byte. Interesting. That's correct. It's not a thing. So why is that where we're writing to? Do we have anything about finish? It's just way too much stuff now. Not that address, but this one. I mean, I think it is that address, so put a breakpoint on this and see if we ever hit it. We do hit it. Okay. I guess it just hadn't been loaded properly or something. So we only need to write this low byte of A0 and overwrite it with main, which has the low byte of ED. So, okay. Then, let's do this then. We'll just hard code this. Because I don't know if there's a way to statically figure out what that first thing is. Let me do we have like let me get the address. Oh, no. I want not Finney, but Finney array. Okay. So we can do that. We need binary dot. I guess I do need to look into it again. Can I get interesting? Get segment for address. That's not what I want. Oh, maybe there's just Finney in here now. Oh, these are the like settings for TechSec. Okay, so get section by name dot header. Okay, that works. And then penny first pointer, let's say. Section. Gets that. I really gotta. What do I do this on? Yeah. Okay. Bin dot section. Okay. So I don't need that. I do need bytes. The first 4 bytes. Okay. Then what we need to write is byte is main adder B0. We happen to know that ED versus A0, so main is higher up, minus Finny first pointer 0. So that's the byte that we want to write. And we're still going to append Finny adder. Then only the word. The padding is going to be how do we figure that out? What is the byte we need to write? Minus how much we have already written. And then 2 to the 8. Oops. I don't think subtracting it like that is going to work. Simply because we need to. So if we've written let's say that, then the byte we want to write is, oh, well, the byte we want to write is just what is already there. We don't actually care. Yeah, so we don't need that stuff. Okay. Then, so it's going to be ed written that much. Can we take that much mod 100 or mod okay, so byte minus that maybe. Sure. I mean, it's going to be the same difference, right? But if we then take that amount, add it to what we've already written, and then mod that by and what is byte? Okay, so that is the amount that we want to write. Our padding is byte minus what we have written. Well, we can give it a shot. And then I'm damn close to having to leave. Oh, too many formats maybe? Oh, well, certainly we don't have an I, so I think we're good there. Okay, and then in theory we only need to write 14 more bytes. No, sorry, 233 will wrap us around. So we will have written 4 mod, or whatever mod 256 is for. Well, that's interesting. Okay, so let's break, you know, just clear out the breakpoints. I'm sure there's a good command for it in GDB, but I don't remember. Okay, so we're going to break on main plus 98. So we'll check that our first write to override stir-char to system in the GOT is working. And then we will also, I guess we'll just check at the same time whether the finish array worked. Okay, so if we look at what we've got in the finish array, that's the original address. And then this is the address for the GOT for stir-char. And if we step over that, we have written the wrong thing. We are off by 1, maybe? No. We're just writing the wrong value now? To just redo that, I guess. Oh, okay. Right, because we're not going to write 2 bytes. Or we're not going to do 2 writes for that one. Okay, double check that. Double check that there. And then NI and first thing, that is correct. And that is correct. So, okay. Right. So we want to receive until the smiley face. Actually, is that what we want to do? No. Here we want to do receive until the prompt again. Then we'll send our line and then print everything else. Hey! Can't believe that worked. I don't know who's just joined back in, but you got here for the moment of success. And I have 5 minutes before my Zoom call. But I can real quickly go over what I ended up doing. So on our first time through main, when we do the printf, we do our memory corruption, and we choose to overwrite strchar with the address of the PLT entry for system. So if we ever come back and run get nline again, it will have just done a fgets call, so it would have taken input from us, and then that input is the first parameter to strchar, so it becomes the first parameter to system, so our input gets passed to system so we can run our shell command. So that's the first piece. Then the second piece is that we overwrite that finish array pointer, so that instead of running whatever normal closeout, run all the like destructors for C++ code, because technically this was compiled as C++ code, I think. Certainly links to C++ library, I thought. Or no, I'm thinking of something else, but it runs some like standard destructor thing. So we replace that with the address of main. So then we rerun main, which calls get nline again. So then we get our second round of input, and that gets passed directly to system. And that's what the script does. So overwrite the PLT, or overwrite the GOT pointer with the system PLT address. Then thankfully we only have to overwrite the last byte, the lowest valued byte rather, of the address that's in the Finney array location, because when I was trying to do it where I was overwriting the whole thing, the payload was too long. So just overwriting that one low byte works because they share all the other bytes. And then, yeah, we send that in, wait for the prompt again, and then we send our command and that's now passed to system. So cool. Real quick, I want to just run through, gonna like scan through this and see if they did the same thing. Okay, so rather than put main in there, they put get endline. That's fine. And then they chose to put system for Sterling, I think. Yeah, okay. So they did basically the same thing, slightly different choices of where to jump to for stuff, but otherwise it's the same concept. So cool. I'm glad that I was able to, I got to a point where I was really stuck because I didn't think that I could do something with the functions that run on exit. But I should have dug into that more. But having seen that bit in the write up, I just was able to work out from there what needed to be done. So I feel really good about eventually getting this. This was definitely a more involved challenge than I expected from the format strings, but overall I enjoyed it even with all the frustration. So thank you for joining me. I'm going to have to quit out like right now because I am going to be late. So thank you all for watching the stream if you're watching, and we'll do another one tomorrow.